In this video, I want to show you how you can check your parametrizations using a graphing calculator. These are going to work for paths in the plane, just in 2 dimensions in terms of x and y. So it's not going to help you with the 3-dimensional, but it is certainly a good useful tool for checking your work. We want to look at again at this path going from the point 0, 0 to the point 2, 4 along the curve y is equal to x squared. We can sketch this vector valued function, this parametrization, by using our calculator. You want to make sure your mode is in parametric mode. We've introduced a parameter t here, and that is going to correspond to parametric mode in our calculator. The path itself, r of t, is equal to ti plus t squared j. We let the components equal your x and your y. So if x is equal to t and y is equal to t squared, we can do a standard zoom here and look at the path. We see the path is going along this right side of the parabola, which it is moving along that path y is equal to x squared. And what you also want to do is check your time interval. If you press trace, you'll see at time equals 0, the location is at the point 0, 0. That was our starting point. And then if you type in 2, t equals 2 and enter, you see that after that 2-second interval, we are looking at the location 2, 4. So that's one way of checking to see if you are on the right path in terms of coming up with a parametrization. Let's look at this second example we did, where we came up with a parametrization along this path here, moving from the point 1, 4 to the point 5, 2. We came up with this parametrization using the equation for finding the equation of the line and then setting up your start time and your end time. So what you want to do here again is using parametric mode on the graphing calculator. I'm going to set the y equal to, go to y equals and set your x equals t. And then you set your y equal to the equation, what the y was equal to in the equation of the line, introducing that parameter t. You want to put the negative 1/2 in parentheses using the division. T, I'm going to delete that actually. Begin again, negative 1/2, oops. Negative 1/2, close the parentheses, t plus 9/2. And then I'm going to go to my standard zoom, zoom 6, and you see a portion of the line. We want to make sure that our time interval that we came up with from 1 to 5 will bring you to the start point of 1, 4 and then to the end point of 5, 2. When you press trace and type in, we defined our time interval to start at time equals 1. You can see the location is at 1, 4. And then when you trace and type in 5, you see that the ending location is at the point 5, 2. So that's one parametrization for that path. And if you recall in the last video, we actually came up with an alternate parametrization for the path. Let's look at this. Okay, so this was our x of t and y of t, and the time interval here was from 0 to 1. Let's check that with their graphing calculator. Going to in parametric mode on the graphing calculator, in this case we're going to let our x equal the 1 plus 4t. And then I'm going to clear what I have in there for y, and the y was equal to 4 minus 2t. And then I'm going to do a standard zoom and look at the path here. When the time interval that we came up with was time equals 0 to time equals 1. So when we trace and we type in 0, we see the path is starting at the point 1, 4. And then when we trace and type in 1, we see that this path does end up at 5, 2 in only a one unit increment of time. All right, let's look at this next example and find a parametrization that would take us on a path that is going around an ellipse. So we can make a quick sketch of the ellipse. It's in the form of x squared over a squared plus y squared over b squared is equal to 1. So we are going to go 4 units to the right and left of the origin. And then we're going to go 3 units up and down. So the path is this elliptical path. And to come up with a parametrization, to introduce another parameter here, we're going to be using trig functions. And the reason why we're going to use trig functions is that there's a common trig identity that we see all the time. That identity is sine squared theta plus cosine squared theta is equal to 1. In this case, I'm going to use t here. Sine squared t plus cosine squared t is going to equal 1. We know that that is a commonly used identity, or sine squared theta plus cosine squared theta is equal to 1. So what I'm going to do is see the similarities in this equation of the ellipse with this identity, where we have x squared over 16 plus y squared over 9 is equal to 1. Well, what I'm going to do is I'm going to set the sine squared t equal to x squared over 16, and then I'm going to set the x cosine squared t equal to y squared over 9, and I'm going to solve them for x and y. So I'm introducing that parameter t. So if I set sine squared t equal to x squared over 16, I can simplify this by taking the square root of both sides, and I get sine t is equal to x over 4. I just took the square root of both sides. And then multiply by 4 to get x by itself, and you get x is equal to 4 sine t. Now I'm going to set this cosine squared t equal to y squared over 9. And then I'm going to take the square root of both sides of this, and I get cosine t is equal to y over 3. And then I'm going to solve this for y. Y is equal to 3 cosine t. And then I need to determine a time interval that would make a complete path here. And typically with these trig functions, the time interval is going to be from 0 to 2 pi. So these are going to be our parametrizations, and then our vector valued function, r of t, is going to equal 4 sine t I plus 3 cosine t j, and the time interval will be from 0 to 2 pi. Now that's one approach, not the only one. These parametrizations are not unique. You can actually come up with an infinite number of these. In fact, if you were to initially begin this with the cosine squared t plus sine squared t, you could have an alternate parametrization, which you may end up seeing more often by letting the x equal cosine, because you have that conversion equation. You could also have 4 cosine ti plus 3 sine tj for the same time interval. Now if you sketch both of these, you'll see that the path is an ellipse. The only difference is in the orientation where your start and your end time is.